Just give me a moment. Great. Thank you all so much for joining today's webinar on hurricanes and extreme precipitation. This is the third webinar in our series covering various aspects of climate change in North Carolina. And I'm really excited that today's topic is something that I find certainly personally relevant. And based on that chat, a lot of people are as well. I did want to share that today's webinar, as well as all the webinars in this series, are being co-hosted by my office, the State Climate Office of North Carolina, and the North Carolina Institute for Climate Studies, or NCICS. And we've been working together for a little over a decade now on various climate projects in North Carolina, including this webinar series. And I wanted to share some of the ways to stay informed about current weather and climate research in the state, as well as ways to just see how current weather events like hurricanes or flooding might fit into that historical climate context. So the first of these is the North Carolina Climate Blog. I know a number of you are probably subscribers to this. This is run from the State Climate Office. We post about twice a month, and most of these posts are written by Corey Davis. I should give credit to him. He's an excellent writer. Does
you can't do it.
And you can follow that URL there to sign up and see the post, and also put this in the chat. And then I wanted to introduce Tom Maycock from NCICS, who will talk a little bit about their research highlights page.
Thanks, Rebecca, and thanks for everyone for joining us. We're here in Asheville, and we do a range of climate research working with NOAA's National Centers for Environmental Information. And if you're interested in a little deeper dive into some of the science, we put this link to our research highlight collection. And this is where we have web stories highlighting individual research papers, and you'll find a number of them over the last couple of years related specifically to precipitation and hurricane issues. So they're written for, hopefully, to work for sort of a general audience with links to the actual papers if you want to really dive into some of the research. Ken Kunkel, who'll be speaking in a bit, you'll see several papers he's worked on, I think, highlighted there, so you may find that interesting. I guess ready for the next slide. So a little Zoom mechanics. Those of you who have joined us before are familiar with this, and probably most everyone is with Zoom at this point. Please try to stay muted during the speakers so that we don't have any background noise. That's a little button in the lower left hand of your screen. We'd invite you to ask questions at any time during the talks in the chat window. And we'll be kind of collecting these in a Google Doc, and then we'll sort of raise them with our presenters and have them answer them verbally. And we'll also be collecting all these notes along with other resources to be published on the website along with the recordings. And we'll also have time for Q&A at the end if you want to speak up on video or audio. But feel free to put your questions in the chat blog at any time. And next. So we have three speakers lined up for you today. First is Ken Kunkel talking about Hurricane Florence, and is that sort of a picture of what we can expect in the future here. Dr. Jared Bowden talking about future design storms for resilient infrastructure, and Dr. Barbara Dahl talking about alternatives to improving resilience to riverine flooding in the eastern part of the state. And we'll go through those presentations, and we'll take a real short break, and then we'll open it up for sort of interactive panel discussion, address your questions and any other new questions you want to bring up. And so we'll kick off with Dr. Ken Kunkel. If you were at our first session, which was an overview of the North Carolina Climate Science Report, you've already heard from Ken. He led the development of that report and leads many of the activities and the sort of foundational science for the national climate assessments. Precipitation and hurricanes are a special focus of his research outside of those projects. So he's a really good candidate to talk to us about these issues in North Carolina. So we'll hand it over to Ken and talk about Hurricane Florence.
Thank you, Tom. I'll share my screen here and get started. Okay, I hope it's all in full screen mode now. Okay, good. I'm just going to jump right in here, talk about Hurricane Florence, and start out with showing the track of Florence. Florence started as a tropical low pressure system off the coast of Africa, and it just steadily moved across the Atlantic, varying in strength during during its travels. As it approached the coast of the United States, it was a major hurricane for a while, but it did weaken some before it made landfall. And if you look at the inset panel, you can see its landfall in North Carolina in a little more detail there. And most importantly here, as it approached the coastline and then as it actually made landfall, it slowed down quite a bit and slowly moved southwestward along the coast and eventually through South Carolina and then finally veered to the north and dissipated. So the critical part of it is that it did slow down and cause a few days of very heavy rainfall in North Carolina. Well, where did the rain fall and how much? Here's a graphic that I did, or the data analysis I did for, looking at rainfall over the period of September 14th to the 17th in 2018. Each of these is an individual station that reported on each day during that event. If you look at the right-hand legend there, you see that the black dots are 0 to 5 inches, the green are 5 to 10, kind of blue-green 10 to 15, dark blue 15 to 20, then the orange 20 to 30, and the red are greater than 30 inches. So the big amounts fell in southeastern North Carolina. You notice a number of locations either in orange or red, indicating over 20, in some cases over 30 inches of rainfall. Going outward from that core area, quite a few locations had between 10 and 20 inches. And then further out, a number of places had 5 to 10, including the Raleigh-Durham area. This is another view of the rainfall patterns. This was produced by the National Weather Service in a report they did on Hurricane Florence. And it tells the same picture, really, in a different way. The heaviest rainfall there in the southeastern part of North Carolina and surrounding parts of South Carolina. And once again, there were a number of areas that had more than 20 inches of rain over 3 to 4 days, really torrential amounts of rainfall. If you look at the point totals, the largest amounts, both Elizabethtown and Lumberton had nearly 36 inches. Swansboro had about 34 inches, and then there was a site near Wilmington that had over 31 inches. So you're talking, almost 3 feet of rain, 2.5 to 3 feet of rain over this 3-day period. If we look at a breakdown by day, this is from the Wilmington, North Carolina airport. They didn't get quite as much rain as the one station did near Wilmington, but still impressive amounts of rain. The heaviest rain fell on the first day of landfall of Hurricane Florence, where they received nearly 10 inches of rain that day. And then the following 2 days, also torrential rains, although not quite as much, 7.5 inches on the following day, and then about 4 inches on the third day after landfall. So how does this event compare historically? And I'm going to both take a national and a state perspective on this. I will start with a national perspective. And what I did was to do an analysis of 70 years of rainfall data from 1949 to 2018. And what I was looking for in this were kind of comparable events to Florence with rainfall over a few days over a large area. So I was not interested in, I was interested in the point amounts that were very heavy during historical events, but more so how much rain fell over a large area. And that's really the key determinant for flooding in streams and rivers. It's not just a single point, it needs to be over a large area. And what I was looking for are the largest multi-day rainfall events over the entire US. So I did this analysis. I identified the top 100 events for that period of time. The next graph is going to show you a ranking of the top 30 events out of that 100 events. So first rank 1 through 30, and it's going to show the amount of rain in each of those as a function of rank. Rank will be on the horizontal scale, rainfall will be on the vertical. So the far left-hand side will be rank 1, and then going down to rank 30. So this is what it looks like. And the thing that should strike you right away, and when you do these kinds of analysis, you kind of have to specify an area that you're looking at. And so I specified an area of 20,000 square miles. That's about roughly 140 miles on a side, if you want to look at a box that represents that amount of area. Okay, so Hurricane Harvey rather, in 2017 had 24 inches of rain over a 4-day period, and that's averaged over the entire region of 20,000 square miles. So think about 2 feet of rain covering an area 140 miles on both sides. Hurricane Harvey is by far the largest event in the historical record for the US. Then it's like almost 50% higher than, well, about 40% higher than the rank 2 event, which is about 16 inches. Hurricane Florence was no slouch in this kinds of analysis. It ranks number 7 for events over a 4-day period, 20,000 square miles. So really, from a historical perspective, Hurricane Florence is a really outstanding event in the sense of what nature produced during that event. Now, if we look at a little smaller region, in this case, 14,000 square miles, so getting down a little bit in size, Hurricane Florence was perhaps a little bit small compared to some of these other historical events. So when we go down to a smaller area and kind of pick up the peak rainfall for Florence, it actually ranks number 2. Harvey is again number 1. Anytime we do these analysis, Harvey is at the top, and usually by a large margin. But Florence is number 2. So once again, this really was an historic event in the US climate record. Okay, if we go back to the 20,000 square miles and we look at the top 10 events, this gives a listing, when they occurred, where they occurred. In the cases where they were associated with a hurricane or tropical storm, the name of that storm is given in parentheses in the far right-hand column. And what I'd like to point out there is that of the top 10 events, 5 were from a hurricane or tropical storm. So certainly in these really, really big events, hurricanes are really very important weather phenomenon as a cause of the most extreme events we've experienced in the United States. Oh, just one last thing that if you want to look at this, where they occurred, almost all of them are occurring in the kind of Gulf Coast region. But there are events along the West Coast, and of course, Florence is an event that occurred along the Atlantic coast. If we look at where these 100 events are distributed across the US, this figure shows that the majority of them are in the Southeast US, with a lot of those right along the coast, Gulf Coast. But there are a number of events along the West Coast, winter storms that can cause massive amounts of rainfall as well. Okay, what about how are these events distributed over time? Are they kind of randomly distributed over the 70-year period? And the answer is no, that in the most recent, this is a graph that shows the number of these 100 events that occurred in each 10-year period in the 70-year record that I looked at. And if you look at their distribution over time, it's kind of up and down in the last few decades, but there seems to be an upward trend. There are lower amounts in the first roughly half of the record I looked at, and the seemingly upward trend in the latter part of this, such that the last 10 years in the analysis I did, in the period of analysis, had the the largest number of these 100 events. Okay, what about the state? Well, if we look at North Carolina and look at the events, just extract the events that occurred in North Carolina, Hurricane Florence is the top one. That would be evident from the table I produced of the top 10. Florence is the only one in North Carolina. In North Carolina, the second ranked event is Hurricane Floyd from 1999. But Hurricane Florence produced quite a bit more rainfall than Hurricane Floyd. Okay, now let's stand back a little bit and just look at overall trends in extreme precipitation. I've done a lot of analyses of this and produced some graphics for the Fourth National Climate Assessment, which I'm going to show right now, about what's been happening both over time and over space, basically geographic distribution of heavy rain events. So this is a graphic from the Fourth National Climate Assessment, and it shows the number of heavy rainfall events. It turns out to be, in this case, essentially 5-year storms, events that occur on average about once every 5 years, and 2-day events. So we're looking at, kind of 1 to 2 day heavy events that, again, occur about once every 5 years. And how many of these have occurred over the US in each 5-year period? I've got these distributed now in 5-year chunks. And what we see here is that beginning around the 1980s or so, the frequency of these events began to rise, and they've been rising ever since. I actually started heavy rainfall studies around 1990, and quite a bit's happened since that time in terms of the changes in the climate of the US. And it turns out over the whole globe. The last 10 years in this analysis have the most or the highest number of these events. How's this upward trend distributed geographically? Well, we've broken this down into 7 regions over the US, over the contiguous US. And the numbers in circles here give the change in the number of events over this entire period that I illustrated in the previous graph, a 116-year period. So if you look at these numbers, you see that in the Southeast US, we've experienced a 58% increase in the number of such events. Interestingly, we have very large trends in the eastern part of the US, but the trends are much smaller in the western US. And even in the southwest US, there's actually a slight downward trend. So there are interesting geographical variations in the trend patterns that we see in the observational record. So what about the future? Well, we can make some statements, and if you were here for the talk I gave on the North Carolina Climate Science Report, you might recognize these first 2 statements in particular, because they're basically statements we make in that report. So the first one is about global temperature. And our statement in the report is that it's virtually certain that global temperatures will increase if atmospheric greenhouse gas concentrations continue to increase. So we've seen quite a bit of warming globally as greenhouse gas concentrations have risen. And just on the basis of both this historical observation and basic physics, we contend that it's virtually certain that temperatures will continue to rise. For North Carolina, we've our statement in the report is that's very likely that North Carolina temperatures will increase if global warming continues. So it's a little bit lower certainty. We're not saying virtually certain, simply because what we observe globally is that while temperatures globally have risen, there are some geographic variations in the amount of warming, the rate of warming that's occurred. And so when we get down to a local level, like North Carolina, our confidence is maybe a little bit lower, but we're still fairly confident that temperatures will continue to rise. So then the follow-up question with regard to this talk is, how will extreme precipitation respond to those warmer temperatures? Well, this is a graph that illustrates some of the basic principles that we can examine when we think about this problem. And what it's showing is that how the atmosphere might respond to global warming. The graph on the left is a graph showing model estimates of, or model projections of temperature increases under a very high emission scenario. If we continue to accelerate our emissions of greenhouse gases. And it has two possible changes to our climate. One is in water vapor content. Turns out that a basic physical principle of the atmosphere is that the amount of water vapor that the atmosphere can hold increases by about 7% per degree Celsius, or about 4% per degree Fahrenheit. As we increase temperature, the capacity for the atmosphere to hold more water vapor increases, and that essentially does increase the capacity for weather systems to produce heavy rain. Now, global warming has another change in the climate system, and that is it actually can change the meteorology, weather systems that cause heavy precipitation. So these changes in the meteorological systems can change the opportunities for heavy rain. Now, with global warming, there's only one direction that water vapor goes, and that's upward. As temperatures warm, the amount of water vapor in the atmosphere will increase. With regard to weather systems, it's not at all certain which direction they will go. They could increase, they could decrease in number or intensity. So that's a much more uncertain part of this picture that I'm laying out. Okay, so however, when we start looking at historical weather data, and specifically the conditions that are present in the atmosphere when we get heavy rain, the recent research that I've done, and others have done similar research, indicates that the amount of rainfall in the heaviest events is determined largely by the amount of water vapor in the atmosphere. I'm going to show you a graph from a paper that I published earlier this year. If you kind of bear with me with pulling a paper out of a research journal article and just slapping it here in my talk, just give me a minute to explain this. What we did here was to look at the historical record in the US, look at all the heavy events that have occurred, and looked at what the corresponding water vapor was in the atmosphere at the time. And then simply did a statistical aggregation of these results. And this is what we found. In this graph, the vertical axis is the amount of precipitation in the heavy events. And the horizontal axis is the amount of water vapor in the atmosphere. So as we go to the right, as water vapor increases, on average, the amount of precipitation in these extreme events increases. Another aspect of this study showed that in terms of the opportunity, the meteorological systems, that it was important that there was a meteorological system. You have to have a weather system to cause rainfall. However, the strength of that system was less important than the amount of water vapor that was present when that system occurred. So that sort of gets back to my banner here. It's all about water vapor. It's not quite all about water vapor, but it's mostly about water vapor. Now that's really important because then it brings us to the central question is how will water vapor change in the future? And really it comes down to ocean surface temperatures. That will be the primary determinant. Our water vapor source, certainly in North Carolina, and for that matter, in most areas of the US, when you have a heavy event, the weather system is tapping moisture from the ocean, whether it's the Gulf of Mexico, the Western Atlantic, or in the case of the West Coast, the Pacific Ocean. That's the direct tap of moisture that's feeding a meteorological system that is producing heavy precipitation. And we get back to this principle that the amount of water vapor in the atmosphere is a strong function of temperature. And over oceans, the atmospheric water vapor content essentially reaches its saturation value because there's a limitless source of water. You've got a water body right there. So the atmosphere will be close to saturation over the oceans. And as the oceans warm, if they do warm, the amount of water vapor will go up commensurately. So let me now look at how things have changed historically in ocean surface temperatures. So I'm going to take a fairly large view in the next graph, and then a slightly more locally relevant view in the second one. So if we look at the ocean surface temperatures, and that's denoted here by SST, which stands for sea surface temperature, and look over the northern hemisphere over the last roughly 50 years. How have things changed? What I've done is I've taken the ocean surface temperatures and essentially converted it to a equivalent amount of water vapor. And if you look at this graph, what you see is that since 1970, there's been a very steady increase in ocean surface temperatures over the northern hemisphere and commensurate increases in the associated near surface humidity. It's been about 7% over that period of time. It looks very linear in this graph, so you could, in essence, extrapolate out into the mid-century and you get a further 7% increase in water vapor compared to present conditions. Well, what about maybe a little bit closer to home? Let's look at the Gulf of Mexico. So here is a very long time series of Gulf of Mexico sea surface temperatures. And what we find in this view is that sea surface temperature, this goes back to 1895, so really going back back in time. Quite cold relative to the present conditions, sea surface temperatures in the early 1900s, kind of the mid 1900s up until about 1980 or so, fairly steady ocean surface temperatures. And since that time, temperatures have been gradually rising. And in fact, in fact, and you see this is actually during the warm season when we tend to get hurricanes. The top 4 warmest warm seasons in terms of sea surface temperature have been in the last 5 years. So we've had very elevated temperatures over the Gulf of Mexico. That certainly was a factor in Hurricane Harvey, at which time they were actually at a record level. And while it's not certain how much that amplified the rainfall, it certainly had an amplification factor on the rainfall that occurred in Hurricane Harvey. Okay, so now to my last slide. What about future changes in hurricanes? So we know that water vapor will increase. What about hurricanes? Will they become more frequent, less frequent? If you were present at my talk on the North Carolina Climate Science Report, you may remember the answer. And the answer basically is there is no scientific consensus whether the number of hurricanes will increase or decrease in the future. However, it is the consensus of experts who do research in this area that hurricane rainfall will increase because of the water vapor effect if, big if, but right now we're on that track, atmospheric greenhouse gas concentrations continue to rise. So going back to the first, my title of my talk, Hurricane Florence, is that our future? Well, it's certainly, based on our scientific understanding, is the direction we are likely to go. Thank you.
Thank you, Ken. That was a really great presentation. I definitely learned a lot about hurricanes and how we're expecting things to change in the future, and a lot too about the history of heavy events. So if anybody has any questions for Ken, please feel free to type them into the chat, and we'll get to them in just a little bit when we do our Q&A section. Right now, I'm going to just briefly share my screen and go ahead and introduce our next two speakers, Dr. Jared Bowden and Dr. Barbara Dahl. They're going to be talking about some research activities going on in North Carolina, kind of getting more at the what are we doing about this? What are we doing to uncover understanding of how these events are influencing infrastructure and how to respond? So Dr. Jared Bowden will be talking about future design storms for resilient infrastructure. He received a Bachelor of Science degree in meteorology and marine science, as well as a Master of Science and PhD in atmospheric sciences, all from NC State University. And his expertise is in the application of numerical weather and climate models. And so part of his ongoing research emphasizes characterizing uncertainty in changing precipitation regimes for air quality and ecological and hydrological applications. So very relevant for today. And then right after him will be Dr. Barbara Dahl. She's an extension specialist for North Carolina Sea Grant and an extension associate professor in the biological and agricultural engineering department based at NC State University. Barbara holds a PhD in biological and agricultural engineering and is a licensed professional engineer who leads a team of engineers to conduct geospatial analysis, hydrology and hydrologic modeling, to evaluate ecological restoration practices, and to assist communities with identifying flood mitigation opportunities. I'm really excited to have these speakers up next, and I will stop my screen sharing, Jared, and please feel free to take over.
Okay, thank you. So hopefully you can see that now. Okay, thanks. It's a great to follow Ken, because what Ken talked about really leads up to what I'm also doing, and actually Ken's part of a new project with that I'm gonna be talking about here with North Carolina Department of Transportation, and Barbara is also kind of on the tail end of this in terms of the applied sense of this project, and really thinking about, well, what do we do in terms of our infrastructure? We know, as you see on top here, there's pictures of I-40, and you know, I-40 during Florence looked like a river, and you couldn't really even tell that this was a highway. You would probably thought that this was some type of river looking in the top left. And the damage to I-40 on the right-hand side with the amount of precipitation we have. And so the big question is like, well, what do we do? How do we design, and what are we going to do about these problems? In particular, thinking about things like hurricanes. And so the big question is how do we merge the climate science and the knowledge that we have with highway design to ensure that our infrastructure is resilient in the future? And so Ken really gave a really good talk about this, and thinking, well, Florence, that you have to start considering this as like plausible types of situations in the future. This is the knowledge that we have. One of the knowledges that we're most confident in is that the intensity of precipitation would increase in the future as the climate continues to warm, and based on the amount of moisture in the atmosphere. And so so that's basically the part of knowledge that we need to try to figure out, how do we integrate that part about rainfall intensity into resilient design. And so I'm going to talk about that a little bit here, and how do you do that. And so one of the things is that is that the downstream applications, particularly things that NCDOT does, is they need rainfall products to be able to put into their hydrology models, which basically looks at things like stream flow and seeing, okay, how intense, how much flooding would you expect, and things like that. And in terms of specifically thinking about the future and how do you design, one of the things that they use are something called intensity, duration, frequency curves. And Ken talked about the 1 in 5 year storm, or like the 5-year storm. There's like the 100-year storm, the 500-year storm. You know, these are annual exceedance probabilities. Basically, you know, how frequent would you anticipate these types of storms for certain durations? And so what I have on the left-hand side at the very bottom is, on the y-axis is the precipitation intensity, and on the bottom axis is basically the duration. And then you have what's these, you know, 1 in 5 year storms, 1 in 100-year storms. What's this probability of these different storms? And so you go from basically a 2-year storm, and if you were look at, okay, say a 24-hour rainfall event, and you wanted to design, this is actually, I pulled this for Apex, North Carolina, out of this NOAA 14 atlas, and you would say, okay, well, what precipitation intensity or depth, how much rainfall would you expect? And it'd be less than 5 inches. But if you went to say, let's say you want to consider that as a 1,000-year storm in terms of probability, that basically doubles or a little bit greater than 10 inches. And so the thing is how will these design values, for instance, change in the future? And the only way you can really get at this type of information is from a probabilistic standpoint. And to do that, you need many, many years of climate model data to investigate these types of problems. And so this type of activity it can be fairly expensive and computationally and very challenging to address in terms from a probabilistic standpoint with the data that we have. And there's been some push towards how do you scale these intensity, duration, frequency curves into a warmer climate. And I'll talk about that a little bit using this climate model data. A second thing that you can really do is more of idealized type of experiments. And these are using like your numerical weather prediction models that you see on TV at night, and then they forecast out, you know, 24 hours, 48 hours through the end of the week. And then they say, okay, this rain comes through. But one thing is that in these models, you can do idealized experiments with them. And you can kind of try to see, well, how would Hurricane Florence, for instance, look like if those sea surface temperatures warmed, if the atmosphere had more moisture capacity available, and you could have more rainfall? What would that storm look like? How much rainfall would fall from that storm? And so these are idealized type of model experiments that you can then try to think about, and you can try to say, okay, yeah, look, the size of the storm maybe have changed a little bit, or the intensity of the rain bands changed. And you can really look at all different types of things through these more idealized modeling experiments. So I call that the deterministic type of modeling, where you look at a single storm and you kind of see how that storm behaves in a warmer climate, versus a probabilistic standpoint where you look at climate model data, for instance, out into the future and saying, okay, what does the model say from a probabilistic standpoint? And so I wanted to show one of the things that I've been doing, and I've been working with a postdoc at US EPA and some of my colleagues at EPA, and we've been trying to figure out, well, what if you were to look at storms like, for instance, Floyd, Matthew, and Florence, and how would they look at by the end of the century, possibly using this probabilistic standpoint of using climate model data to inform these storms. And so on the top is the observed Floyd, Matthew, and Florence. And basically anything that you see in pink is basically 1,000-year rainfall event. And this is based on those intensity, duration, frequency curves for the duration of the storm, which if you go out like 4 to 5 days for Florence and you look at how much rainfall fell, you're looking at around the scale around 400 millimeters is basically where things really flip the scale, and you get these pink areas, which are basically the 1,000-year storms. And then what we did was we looked at future climate scenarios. And what's really important about this is that this type of data that can be created can be used for downstream applications, such as in the hydrology models. So if they want to know how much flooding can be associated with a given scenario, they can then take these different cases that we're showing down here in the bottom. And so what I'm showing is basically, if you take those durations, different intensity, duration, frequency curves, and you just simply do some type of scaling based on what happens in the future, you can start seeing the amount of pink for not only Floyd, but also for Matthew and Florence, the amount of pink area. And so those 1,000-year events, you can really see that it kind of spreads out. And so much more intense rainfall over a much larger region. And so this is very concerning when you're starting to think about it. And so we're trying to figure out, well, how do you take this type of information and feed it to DOT applications when they're starting to think about building the next I-95 or improving I-95 or 40 and things like that to make it more resilient to flooding. And then finally, I want to talk about this idealized part. And this is a big part of the project that I'm doing now with the NCDOT, and Ken's part of this. And the expert in this is actually Dr. Gary Lackman at North Carolina State University. And Dr. Gary Lackman, he's been doing these pseudo global warming experiments, but basically it's a pseudo method. It's like, what would this storm look like in a warmer climate? And so what I'm really showing you here is on the left is this is historical Hurricane Sandy. So you simulate this storm with a weather model, and then you say, okay, this is historically, this is what this storm really looked like. And then how will that storm change if you take things like increased sea surface temperature, the moisture capacity of the air increases, and you replicate that same storm. And then what you're really starting to see is that the storm intensified quite a bit on the right-hand side. And so you can start to tease out, okay, what does this mean? And one good thing about this is that you can now go beyond just pure rainfall. It's like, if you're concerned with storm surge, for instance, you have things like winds from these models that be able to inform other applications that DOT may be interested in. And so I'll end with this, that there are multiple methods basically behind all of this. So the pseudo global warming, the probabilistic type of methods, so these deterministic but probabilistic methods. And we should consider basically all of these different methods that provide future rainfall data. But we also have to consider the advantages and disadvantages of each of these methods. And I don't want to get into the details of this, but we're working with DOT to kind of help them understand some of these advantages and disadvantages of these different data sets. But ultimately, when you cross compare all of these different methods that provide future rainfall data, and you get a similar answer, you improve the confidence in how the rainfall may change at a regional to local scale. And ultimately, what we really want is better informed future design. And so having these design storms and having some confidence that this is what we should really be thinking about designing too is something we're really trying to work on and understand in this project. And so that's all I have, Rebecca, and thank you.
Thank you. That was really fascinating. I love hearing how we're using science to inform kind of those design and what to do about it types of decisions. And up next, great, Barbara's already ready to go, and I'll let you take over.
Okay, great. I'm going to move quickly because I have a lot of slides. I want to acknowledge my engineers that work on the modeling with me, Dan Line and Jack Kirky-Fox in the Bio and Ag Engineering Department. They're responsible for a lot of the heavy lifting on what I'm going to show you. Our team really does focus on the kind of coastal plain region where riverine flooding during extreme events, like Jared and Dr. Kunkel have talked about, play out to provide really severe problems for these areas. We are trying to help small towns with really big problems, and we focus on trying to understand why it floods and what, if anything, can we do about it? Is there any options? And we use a lot of models and geospatial tools to help us ask those questions. I want to feature just a couple things that we're working on, and I'll show you a web page at the end that provides some more information you can look up. For DOT, we just finished up a 2-year project focused on the Neuse River Basin with a lot of work in the communities of Kinston, Smithfield, and Goldsboro. Our project started off with stakeholder workshops where we had invited elected officials, emergency managers, public works directors, and we listened to them about what kind of issues they were really struggling with the flooding. Where were their needs and where were they not really seeing help or had big questions or concerns? And that led to the actual scope of work for our project, in which we did a number of things. I'm not going to read these out. And what I want to do is just focus on a few things, kind of give you some tidbits about what we did and some of our findings. So first, we looked at a number of bridge crossings of the major rivers. What we heard from communities there is they were concerned that the bridge crossings were blocking the flow of water, and upstream of that bridge, that was exacerbating the flooding because that bridge was just kind of providing a blockade. Water couldn't get past. So we said, well, let's look at that. Let's see if these bridges are causing problems. We looked at 10 bridges across the 3 communities, plus 2 bridges in Craven County, one on the Neuse, one on the Swift Creek. The rest are all Neuse bridges. And what we did is we kind of looked at, before these road crossings and bridges were placed, you had a river there with a floodplain. And what happens is they come in and fill the floodplain, and then they build the bridge across it too. So they fill the floodplain to reduce the span of the bridge and the expense of installing it. So we said, okay, well, let's look at what if we went in, we removed a lot of that fill, we lengthened the span of the bridge, and in some cases we actually elevated the bridge even higher. And we said, what would this do to flooding? Would this reduce that flooding that's occurring that they perceive to happen upstream? So I'm just going to give one example of that. So in Kinston, there were 4 different crossings. So the Neuse River winds its way through Kinston, and there's 4 major crossings of the river here. And we looked at all 4 of these bridges. And so what we would do, for instance, is here at the top, this is the US 70B. It has 2 openings across that floodplain. All this is fill. And we looked at widening that out to a much larger span. In fact, we took all 3 bridges, which were in the 600 to 700 foot span range, and increased them to 2,000 feet in some cases, and as much as almost 3,500 foot for King Street. And what we found is that the change in water surface elevation above there or upstream dropped very minimally. In fact, if you just addressed any one bridge, you had just minor changes of only a few tenths of a foot, and that the only way to have any substantial reduction was to do all 4 bridges. And in fact, we completely removed the railroad bridge in the model, just showed it as what if it was demoed out. And the best we could get was a 1.2 foot reduction in water surface elevation. So that's millions of dollars to upgrade these crossings with very little benefit. And that's what we found pretty much in most of the communities. Only the Smithfield scenario and Kinston could you even have a really noticeable difference of over a foot. But again, that took multiple bridges. And the main reason we saw is that when we're in these really extreme events, the water downstream of the bridge is all stacked up, it's filled up, and it won't let the water to flow out regardless of the bridge in that location. So you get what we call a backwater effect during these major storms. So everything we looked at was during a Hurricane Matthew flow event. And so at best would be about a foot to foot and a half in Smithfield of water surface reduction. So that tells the communities maybe not, this is maybe not the big focus of what you should be looking at. Maybe there's other things we should be considering for mitigation. Another thing we heard from the communities is that ahead of the river flooding, they often experience very severe flash flooding along tributaries in their towns along before that water even gets to the river. And so this plagues a lot of their communities and kind of makes access very difficult. So we looked at 8 tributaries in the 3 communities that they pointed out as being very problematic for this flash flooding. And sometimes they would have flash flooding there even when it's a non-river flooding event where it's more isolated thunderstorms in their area. And so we looked at all the crossings, our culverts and bridges along these creeks. Here's Atkins Branch on the right. It happens to have 7 crossings of that. So we looked at all those. And what we did is we inventoried the crossings. We evaluated their size they're in a model that's existing. We looked at their condition. We obtained existing hydraulic models of these creeks. And then we looked at the transportation importance of the roads that are associated with these crossings. And we looked at alternatives. So where we found there's a problem culvert, what would it be? How would we want to modify that? And we developed a decision matrix to determine if improvements were made, where should they focus their improvements? I'm going to feature the Goldsboro work that we did. In Goldsboro, we looked at 3 tributaries that had 45 crossings on them. 26 of the crossings have flooding in a 10-year event. So that's well below that Hurricane Matthew type event. 6 of them have flooding in a 25-year event because Matthew is about a 100-year storm in Kinston, if you looked at it there. So this is one of those creeks. This is the big ditch. It had 16 of those very undersized culverts. So we went to all of them. We validated their size and configuration. We looked at the condition. Most of them were actually in good condition. This is one that's very rusty and starting to have problems. And then we looked at all the resources in the town, such as hospitals, schools, fire stations, nursing homes, drugstores, all of this. And we mapped this out and used that to rate the importance of that road route that's using that. And then we use this multi-criteria decision analysis to score each culvert based on its replacement cost, what level of service it's providing in terms of a road. Is it just a 2-lane road? Was it 4-lane divided? What type of critical transportation it provided to those different important things like schools and hospitals, and what flood risk did it have? How undersized was it? And then from that, we were able to rank the culverts. We also looked at, well, if we did upgrade it, how would we upgrade it? And what did that mean to flooding? So we tested in the hydraulic model upgrades of these and see, here's the existing water, how much flooding could we reduce and how big will we need to make that culvert crossing? And so then with the prioritization, we would come out with, okay, you've got 45 culverts and in Goldsboro, but these 4, based on that decision criteria analysis, would be the 4 you need to focus on working with DOT to get improved. Because if they went and they said, we've got 26 pipes really undersized, we've got to have them fixed, DOT's like, we don't have the money to do that. But it's more reasonable to look at those 4 priority roads and these culverts and say, how can we get those upgraded? Another thing we evaluated is there came in the conversation with a lot of the agencies this concept of what if we established kind of resilient or safe routes. A lot of these communities are divided in half or even thirds when these flood events come. So what if we took just one north-south and one east-west route like this and made that the resilient route and focused our upgrades along those 2 corridors? If we took that approach, then these 3 locations here would be the primary places that they would say we need to upgrade those culverts and crossings in these locations. We also modeled future storm events to consider what kind of design standards do we design to. And what does that mean to the future in terms of these communities with their planning and their floodplain ordinances? So I want to focus on the part of that where we use the data from Jared and Anna Jalowska with EPA for this part of the modeling. So he showed you those different future storms that they've been looking at. We got rainfall data for different storm events, the 100-year, 500-year, and Hurricane Matthew events in the future. So we got gridded rainfall, and we put those into our hydraulic model. So here's the rainfall data for Kinston, and brown is the actual observed data for Hurricane Matthew. The red is a moderate management of carbon in 2100. So that's the 4.5. So that says if we do something to keep our carbon levels down, we do some measures, that's what the future storm would look like. And then the blue is where we don't do anything. We just keep going like we're going. It's business as usual. We keep putting the carbon out there, and we see how much more rainfall would fall with Hurricane Matthew event if it occurred in 2100. So then we modeled that in our hydrology model. So this blue line here is the actual observed flow in Kinston during Matthew. The orangish red is our modeled version of Matthew. And so then we plugged in those two scenarios of rainfall across the whole Neuse watershed. And so what you see is with some controls, we still have a major increase in flow. And if we look at the no controls, we more than double the flow that would end up in Kinston during a Hurricane or Matthew event in the future. In fact, we looked at also the 50, 100, 500-year storms, and this blue bar represents the flow just under 40,000 CFS that occurred in Hurricane Matthew. So if we look in the future, if we don't do much about climate change or it continues with this warming, we're going to see tremendous increases in the flow down there. In fact, we could have as much as 2 to 5 feet higher water levels during flooding events in these communities with this future warming trend that we see. So this is something that should be considered in the planning of these communities. One last thing I want to leave you with is another project that we're working on is the use of potentially using natural infrastructure such as reforesting areas, installing wetlands to store water, restoring streams, or even temporarily storing water farms and providing compensation for farmers. We're saying, what if we did that out in the watershed of the Neuse River, and what kind of benefits could we see to flooding? So we're doing, this is current work that's funded by the NC Policy Collaboratory, where we've looked at where the opportunities are for installing these practices. We're modeling the hydrology that would result with these changes in the landscape and the river flow, and looking at also other benefits, not just flood reduction, but what kind of water quality benefits we would have, and looking at comparisons of the cost of implementing this with the benefits. So that's all I have. I'm sorry if I went too fast, but
I thought that was fantastic. I really appreciated that kind of cost benefit. How do we then decide as a community where to prioritize? That was really, really interesting. Thank you to all of our speakers. So we're going to take just a short break, give everyone a chance to stretch. I have 11:01, so if we can come back at about, we'll say 11:05, and then we'll finish up the last 25 minutes doing Q&A, and I'll go ahead and just share my screen with, I can do this. If you'd like to go ahead and enter in some questions into the chat or use the raise your hand function, feel free to do that. But we'll see everyone back here at about 11:05. Great. Well, I have 11:05, so we'll go ahead and jump to the Q&A portion of the webinar. We've had a couple of questions trickle in through the chat. I did have one question just kind of from the pre-webinar survey that we sent out, and some people were able to write in questions. So drawing from that, I was going to ask each of the speakers to respond to is just, what are the biggest misconceptions about climate change as it relates to heavy precipitation and hurricanes? If there's anything you'd like to say to that. I guess we can start with Ken, since you went first.
Yeah, I was actually trying to think about that question and couldn't come up with a really good answer. Yeah, I'm going to probably pass on that one. I didn't have any real insights.
So when I think about it, like people, I was asked recently, so this was a very active hurricane year in the Atlantic Basin. And somebody asked me, we are having hurricanes occur earlier in the season. And I don't know, Ken, I'm not the hurricane expert. I haven't looked into this, and maybe you have, but I don't know if there's really any true supporting evidence about like the start, like if there's an earlier start in the number of storms.
Yeah, I think that if you look at it anecdotally, you can convince yourself there is, because there have been, some really early ones. And of course, this year, just a whole batch of them early on. But to base a long-term trend on that, I think it's too early to make any definitive statements on that. That being said, as sea surface temperatures continue to rise, they also are hitting a level that's conducive to tropical storms earlier in the season now than they used to. So in some ways, it's maybe no surprise, but I'd be hesitant to make a statement about a trend yet.
Yeah, I agree. Yeah, I wasn't sure if anybody had done any work on that. I didn't think that there was a definitive statement on
I can't think that there has been. I can't remember one anyway.
Yeah. And another thing that I think that people are starting to think about is you talked about like Florence, and as it made landfall, it slowed down. And so there seems to be, from my reading of the literature, that it kind of supports it, but then it's still, there's some uncertainty as to that the how valid that statement is, especially when you're thinking about the North Atlantic in particular.
Yeah, there's been some research, intriguing research about possibly slowing down of hurricanes, and I think that's there is somewhat of a trend there, but once again, kind of early to make a definitive statement about how that will go into the future.
Okay, well, we had a question come in. Thank you for those insightful responses. A question came in from the chat early on, asking about the definition of torrential rain. Are there definitions for terms like torrential? Colloquially, we kind of associate that with things like a lot. Just wondering if there were either in meteorologically or kind of more from the hydraulic, engineering standpoint.
Yeah, I would, Jared might know something I don't know, but I think that's pretty much a qualitative phrase, a little bit in the eye of the beholder, what's torrential and what's not. There isn't, to my knowledge, a specific meteorological definition associated with that word.
Yeah, I agree. Yeah, I think that's up to the person. Yeah, very subjective term. I think when I think about torrential, it really depends on place, right? So like, you know, if you live in LA versus, you know, Carter County, Rebecca, where you're from, your definition of torrential is very different. So it's a really, depends on the person's perspective, I think.
Great. And we had a question specifically for Dr. Dahl. Has anyone considered reducing flooding by paying farmers to keep their soil covered, especially during hurricane season? And then just added to that, reduce tillage and cover crops rather than bare soil, let a lot more water sink into the ground and keep that soil intact rather than letting both the soil and the water wash into the creeks.
We've seen some of that in Iowa where they're kind of working on soil health, but their motivation's also driven by water quality. And these storms that cause the severe flooding, we're talking about events that exceed a 100-year storm, and often the flooding occurs, the flooding is so severe because everything's already saturated. Sometimes we even get, like it's very wet. We might have a tropical storm and 2 weeks later we'll get a hurricane like Matthew. And so everything's very saturated. So even if that soil is in a better covered, better soil health, it's going to infiltrate more. When we get to these huge events, that kind of some of that is lost. Like we see in our models where areas that are pretty undeveloped start shedding water, nearing the level of a parking lot because it's just so saturated, no more water can go in. So the type of things we're looking at is paying farmers to actually temporarily store water on their farm. In other words, all the rain that fell on that farm would be held with the kind of berming system that would flood a portion of their crops, and they would be compensated for the loss of that crop. So that's what we're exploring now. We're working with others that even working to interview farmers to find out what kind of payments would be acceptable to do something like that.
And kind of we just got a follow up 2 questions related to that. So if the first was from Jonathan Heeples. So if you saturate or flood the farmland, would that also possibly flood country roads?
Well, it would have to be very carefully selected so that you don't flood homes or roads or other, things, undesirable areas. So we actually did extensive mapping for this Neuse project and found all the areas that were suitable for this potential water farming, where you have to have a low slope. It has to be around 1% land slope or less because your berms get so expensive if not. And then you have to have a nice contiguous area that would be able to be flooded, and there's no home, there's no animal operation, there's no road or anything that's going to also be flooded.
Sure. Yeah, that makes a lot of sense. And then the other question related to that was, what about like around parks or play fields? Kind of a similar idea there. Has there been any work
around what? Can you say that again, Rebecca?
Around parks or like your play fields, like soccer fields or things like that?
We didn't look at that, but we did look at forestry operations and forested areas as well, even existing wetlands and floodplains to have potential increase the amount of water stored in those areas through, berming systems that would hold more water in areas where it's okay for temporary storage of water.
Great. It's really fascinating. And we had a question come in earlier. I think this one was directed more towards Jared. Is just thinking about the sort of cross-state sharing of any of the research projects doing on infrastructure, or even sharing some of the data that's being done. I know that you had replied a little bit in the chat, Jared. I just didn't know if you could speak a little bit more to what types of cross-state research and sharing happens related to these sort of DOT projects.
Well, this is a really good question. This project that we're working on, actually, this is the first project I've ever had with the state DOT. So, in my experience, it's very limited. And so Barbara can probably better speak to cross-sharing across state agencies. But in particular, with respect to thinking about infrastructure and resilient design and precipitation, federal highways is actually really big into this and trying to lead the effort in terms of the federal infrastructure of highways like 95 and the big interstates. And so how does that information then feed into state DOTs? And so there is this larger organization that's trying to bring together the state DOTs. But as you know, each DOT is different. And so it becomes much more complicated. And in terms of the types of design storms that we're talking about, those change significantly from one region to another. So if you live in California, and Ken's talking about these big wintertime storms, these are, sometimes we call these the Pineapple Express events, where you get a large plume of water from precipitable water from the Pacific down towards Hawaii and come in to feeds the California. That's a very different type of storm event than you're thinking about with hurricanes. And so these design storms, they really have to focus on the types of events that impact an area, and that, you know, those change significantly across the country.
Yeah, the Transportation Research Board has annual meetings, and they've had some of those focused on resilience. And so there'll be not just people from DOTs around the country, there'll be researchers as well, like Jared, myself, who present about projects they're doing in collaboration with DOT, and to share that information on how they're addressing similar issues. You know, there's a variety, you know, it's very different, very diverse across the country, but so that is something that does get shared through TRB in particular.
No. So we had a question come in from Diana. So on the FEMA flood maps, so are these looking to the future at all? Do you know, or are they still just looking at kind of, you know, historical, basing those maps on historical information only?
Still historical. Now, City of Charlotte did their own flood mapping and looked at build out conditions at least. So they're not necessarily looking at future climate, but they did look at build out. And so like everything growth to the, you know, the maximum, and remapped their own floodplains and adopted stricter standards. Section I didn't present was on floodplain ordinances, and there's a lot of room for communities to improve their floodplain ordinances as well. Kind of hearing this, what, you know, future, these changes are occurring now and the future could bring even worse. So let's look at your floodplain ordinances and think about how you can adapt there.
That's at least encouraging and definitely important to do. So another question that's kind of coming from the pre-webinar survey, and you've each sort of touched on this, but what would you say are those big questions, big research questions related to hurricanes and extreme precipitation and associated flooding that you see us collectively tackling in the next, say, 5 to 10 years? So sort of thinking about what are those research directions you see us moving into and answering.
Well, I think that one of the challenges, I'll step back a little bit from the science itself, but one of the big challenges we have in this whole enterprise is that, as well as we might understand the science, and as well as we might advance our knowledge of science, we still have the big question about what society will do, or how technology will evolve. So in terms of, you know, how to plan for the future, that's always a kind of a really big area of uncertainty. You know, will we find ways to transform rapidly our energy generation from carbon-based fuels to non-carbon-based fuels, and how fast will that happen? Some of it is, you know, technological innovation. Others are decisions a society makes, and that's a level of uncertainty on top of our scientific uncertainty. From the science side, I think that I see the direction of research going. We know that our climate models And it gets back to some of the work that Jared and Gary are doing. When we look at the global climate, we need more computer time to really do a better job of modeling the climate system. The global models are very crude in resolution compared to the kinds of phenomena that cause extreme precipitation. And as we look forward to the future, I'm hopeful that increases in computer capacity will lead to much better models of the global atmosphere, and that we'll be able to truly understand hurricanes, for example, being the big one, where we really need much higher resolution to better understand how hurricane frequency intensity will change in a warmer world.
I would say yes, that building on what Ken said, one of the things they do in the Netherlands is a lot of what they call stress testing. So in other words, if they take their system and they start looking at, well, these scenarios, what would happen, and then they filter that into their planning and design on what their next step's going to be. And there's a lot of interest in that with our infrastructure in this country. And like the work we're doing, it's pretty tough to test a lot of scenarios because we have to start a lot of times with GIS, and we do all that. Then we take all what we learn from that and then we dump it into a hydrology watershed model, right? And we do all that, and then the output from that we have to put in a river flow model. So it's not like you can do a whole bunch of rounds because it's just so much work in between. And plus Jared did all the work with the global model, getting it down to a local. So it's like how to stress test different scenarios is difficult just because the connections between different computer programs and the computing power is challenged. So being able to better integrate different types of models and expertise together, like this is the first time I worked with climate scientists at all to, do this rainfall data. So more of that and being able to figure out how it can look and repeated runs and learn, like machine learning from that.
Yeah, Barbara, that's a really good point. When I think about like the state of the science and climate science in general and where it's going, computational capacity in climate models is definitely needed to answer questions like changes in extreme precipitation, and we know that for a fact. How we do that is very complicated and very expensive. On top of that, we have to figure out how to integrate these problems and not be so siloed. And so a lot of times we get focused on a given problem, like, well, how does the number of storms going to change? But really, ultimately, where society needs to know is like, well, what does that mean for a given sector, for instance, transportation? And so integrating the science, and that's what I'm trying to do is I really want to try to figure out how do you integrate climate science and the knowledge that we currently have with various aspects. That includes things like air quality, and you can think about things like ecology and species status assessments and things like that. We know species are kind of are impacted by climate change, and so you have to start thinking about, well, what knowledge do we have that we can then take and bring to those different disciplines.
Those are really, really great answers to that question. And I think really highlight just, it's not something that can just be easily tackled, right? There's no like one question, then we've solved it. There's a lot of different moving pieces that we need to focus on. So our time is getting short, so I just had one final question. There's a lot of really great things that you're all working on. Is there a way that we can stay informed or get connected? Whether it's a newsletter kind of thing that we can follow, like we mentioned at the beginning of this webinar, or if there's even ways to participate in some of your research projects.
I have a web page that I'm going to pull up, if that's all right. And so some of the stuff that we're doing, it's not comprehensive, but we're starting to put it on this North Carolina Coastal Rivers Flood Mitigation page, some of our reports, some of summaries and things like that. So that's if you want to go to that, you can start. I need to keep adding more, but here's one location for some of our work.
Thank you. And I just dropped that link into the chat. So
Okay.
you can follow it.
You know, Rebecca, when I think about citizen science, and how can people participate, there's a really great program that the State Climate Office does. It's like works with the Cocoa Raws, and I really think that so one thing that I know that, for instance, state DOTs and federal highways is working on is we talk about this infrastructure and intensity, duration, frequency curves and updating these curves. The thing is even the data that's being currently used is old. And one of the things that citizen science plays a part in is developing these intensity, duration, frequency curves. And if you, for instance, have a rain gauge in your backyard and you report it daily, that data may actually get used within a framing perspective of updating these curves. And I know North Carolina, for instance, may be participating and thinking about how to update, because we've had recent Matthew and Floyd, and this data isn't really considered in terms of what these current intensity, duration, frequency curves design standards are. And so I encourage others to think about things like Cocoa Raws.
Thank you for mentioning that. And I always appreciate a shout out for Kokoraz. I need to check my gauge. It's been a few days, but and Darian Bertrand, I think she's still on, is one of the co-state coordinators, and she works at the State Climate Office. I'll make sure to include the coordinator email in my follow-up email to everyone. That way, if anyone's interested in joining and finding out more, you can get in touch. Great. Well, I will just kind of wrap things up here. I think you can see my screen again.
Yep.
Great. So I just wanted to share just in the last couple of moments, plug our upcoming webinars. So we're now halfway through the 6-part series covering different aspects of climate change in North Carolina, getting into some of the science that's in the North Carolina Climate Science Report, as well as some of the research and activities happening across the state. The next one will be on November 5th, covering drought and wildfires. And then following that in December was sea level rise, and then one on how to talk about climate change. All of these are being recorded, just like the one today, and they'll be posted on our website. That URL is at the top. I'll also be sending a follow-up email to everyone who's here who had registered with a link to that once it's posted. There'll also be a link to a short evaluation survey. This is just to help us, make sure that we're making this really, truly useful for you, and will help us as we, move forward for the next couple in the webinars. And I think that's the last thing I have. So we'll end it here 2 minutes early. And if you have any questions, for me, I'll stick on for just a couple of moments. But with that, we'll end it here. And thank you again to our 3 speakers today.
Thank you, Rebecca.
Thanks, everyone.
Goodbye.
Hey, Rebecca, it's Diana. I put in the chat box, the December 15th date is actually showing up as December 1st.
Uh-oh, okay.
And I did the registration for it, in it, the bulletin or whatever it is, as being December 1st.
I will, thank you for letting me know. I will go and fix that.
I was going to double check with you which date it really is.
Yes, it's the 15th, so.
I don't to it. I was wondering, and this might be something that the State Climate Office is interested in, or Barbara, or one of the others. The new affirmative maps.
Sorry, it's cutting out just a little bit for me. Can you say that again?
FEMA flood insurance rate maps, which is redundant because you're repeating maps when you say that. They change about every 5 years, and they go through what's adopted and then what's proposed, and then the community gets to argue about the proposed changes. The ones that are enacted are the ones that are enforceable locally. So I don't know how some areas are putting more stringent ones in, because I've had that conversation with the city of Jacksonville planner. Trying to go above and beyond gets politically difficult.
Yeah.
And the question I have is, has anybody looked at past maps? Because if they change or get readopted every 5 years and areas expand, have they looked at the areas of expansion and compared that to changes in rainfall events in those locations, and then try to look to the future to predict what they will? Because planning for future events by using past data, people get very upset when they get flooded out and they were told they did not need flood insurance.
Yeah. No, that's a really good question. I don't know if that's been done to look at that, but I'm going to write it down and see if I can see if maybe Barbara has an answer or could point me in the right direction. I mean, I know I live in a flood zone, and so yeah, I have flood insurance, and we got flooding near our house during Matthew, and right, we were kind of like, oh, whatever, it's no big deal. But our neighbors who were not in the flood zone, they actually got like closer flooding to their house, and they didn't have flood insurance, and so they were very upset, right? I think realistically so. And so just thinking about how that, if that's all, yeah, there should probably be a little bit more exploring that and understanding.
Especially if you're in that location. So what they have to build to the minimum standards of the current maps, but the projected map is going to have it be a flood zone and they're going to be in danger, then it doesn't really make a lot of sense. So I talked to somebody in Pender County who was really upset because he specifically requested looking at properties when he bought his house that were not in a floodplain, and they weren't in the current issue, but they were in the proposed, and the realtor did not show him that. And he bought the property and he flooded out, and he was mad. Yeah.
I was going to mention one thing that a couple of folks that we've worked with are involved with this First Street Foundation, which is firststreet.org, and they're sort of a nonprofit, and they just came out with a sort of new set of maps of flood risk. They got a fair bit of attention. There's a story in the New York Times, and they've taken some pretty detailed elevation data and climate change, and they're trying to put future projections into this flood risk. And Realtor, I'll put it in the chat. Realtor.com, as you can see on their homepage, incorporates this now along with the FEMA flood maps. I'll tell you, one of the interesting things about it is, there are limits to the resolution of the topographic maps that go into this. And so in our neighborhood, the houses just around the cul-de-sac from us are shown as like an extreme flood risk because there's a creek down the hill, but they are way above that creek. And if that creek were to flood massively, it would go over the road on the other side. I mean, there's almost no chance that their house would actually be flooded. So there are limitations even to, serious efforts to incorporate climate change and lots of other data into these things. But it's going to become a bigger, issue and challenge. And so you can go to realtor.com and look up, you can see sort of both sources of information side by side. I think that's going to become it's going to become a real challenge with people trying to get accurate and future forward-looking information about that risk. So it'd be interesting.
Yeah, and it kind of feels like when you buy, my limited experience, and I've only ever bought one house, but thinking about future development, that's kind of something that you always want to pay attention to. Is my nice backyard going to be backing up to strip mall someday, kind of thing. But the other sort of flood risk, future flood risk, and how that is something that we could maybe make easier for people to see.
Yeah.
I'll make sure to include that firststreet.org in the follow-up notes.
Yeah, being down here right along the coast and working with a lot of very flat areas, when people buy the property, it's not a day where they've been having a deluge, and they get mightily surprised when water surrounds them and they're trying to figure out. The other thing I get to talk to people about is water is lazy and it likes to flow downhill. So if you flatten your yard out, the water doesn't know where to go anymore. So here, topography is so minimal that that little, 4 inches or 6 inches becomes vitally important in telling them. We have people that don't like the edges of the property a little bit lower and wet, so they go and add soil there to flatten out their yard, and then their yard. Okay. So
Yep.
we do education on that, and just as a general thing, especially in the coastal plain where we have such flat areas, the importance of making sure that that water continues to know where to go and can get.
Yeah.
But thank you, everybody, and I'm going to sign off.
Thank you, Diana. Always ask the best questions. So I appreciate you attending today.
Yeah, that's good stuff.
All right. Well, thank you all, and I will end the webinar. And I appreciate you sticking all around for the extra couple of minutes to hear the answers to our questions. So.
Take care, everyone.